Okay, there we go. So the topic for today is what happens when we have a telescope, a radio telescope, which has several antennas. And the main reason to have this topic this week is because next week we will be visiting the Allen Telescope Array, which, as you know, is an array of 42 dishes in Northern California. So today we're going to see how beamforming and also interferometry work. The material is in the GitHub here in the beamforming folder, and I'm going to begin with this beamforming demo. I already have this open in GNU Radio Companion, and the way I'm going to work is to have this open, but I'm going to work from scratch. However, I will copy and paste some of the blocks from here just to save time. So let me begin by beamforming demo 2. I'm going to give it a different name, and then I can save. Okay, and I want the sample rate to be 1 megasample per second. This is just a simulation, so you could use any sample rate you wanted, but 1 megahertz is fine. And then I'm going to copy all of this and explain what this is about. I guess I need a few of these blocks. Yes. So, and what else? I also need to import NumPy. So the idea here is, let's say we are receiving an astronomical signal. It could be any type of signal. It could be a quasar. It could be a spectral line. It could even be a technosignature. And to play the role of this astronomical signal, I'm going to use a wideband signal generated with this noise source and the polyphase arbitrary resampler. So let me quickly demonstrate how this looks like. Good GUI frequency sync. And let's see. No, I want to show disabled blocks. Okay, there we go. Maybe I want a third block as well. And let's make this 4096. So this way of generating a wideband signal we already saw in one of the previous tutorials. What we are doing is we are generating Gaussian noise, and then by using this polyphase arbitrary resampler, we resample the noise, and hence we set the bandwidth of the noise. So this is going to play the role of the astronomical signal. The reason I'm using a band-limited signal, which means that it only occupies this part of the spectrum, is to make things easier to see. Most astronomical sources are wideband signals, and they usually occupy much more spectrum than our radio telescope is able to receive. So what would happen in that case is the noise from the astronomical source would occupy all the instrument passband. And I can even change parameters here. So I have the wideband signal bandwidth, and I can play with that. And I guess I could even make it like so. So like this, it would be as a quasar, for example, which is one kind of astronomical source that occupies the whole spectrum, or the whole spectrum we care about. And we can make something rather small. Let's see, this is in kilohertz. So like this, it could be some kind of spectral line that only occupies 10 kilohertz, or maybe some kind of technosignature, which is limited to 10 kilohertz. So that's the wideband signal we're going to use as the astronomical source. We can also set the SNR here. So this is just the same we've had on previous tutorials. What I'm missing here is the noise, and I will talk about it in a little bit. So I also have a GUI entry to set the signal frequency, and this is currently disabled. It's 50 kilohertz in here, but you can see this is at 0. So The reason is because I'm doing this trick of signal source cosine 50 kilohertz multiply. So this, as we have seen, is a frequency translation. And if I use this, then this is centered at 50 kilohertz. So nothing new, really. I have here a virtual sink for my astronomical signal to make things more tidy in the flow graph. And then what the thing we want to do now is to pretend we have two antennas to receive the signal. And one thing that is going to happen is that when we receive a signal, we not only receive that particular signal, we also receive noise. We have seen many examples of that, in particular with the RTL-SDR dongle. Even without any antenna plugged, we received some noise, and the reason is because of the electronics of the receiver. So let's think I have two antennas or a radio telescope composed of two receivers. Then each of those receivers is going to have its own noise because it's generated by its own electronics. By its own, I mean that the noise from antenna 1 is uncorrelated with the noise from antenna 2. And that will become important when we try to do beamforming or interferometry. So I could use a noise source as we have done in the past to add the noise to the signal. But since I also want to do more things, such as changing the frequency of the signal, I'm going to use a channel model block, which is intended to apply changes in the signal that often happen when the signal is transmitted from one transmitter to a receiver. One of those changes is adding noise, and as you can see, one of the parameters here is noise voltage, but there's also frequency offset. And for example, the frequency offset could be caused by Doppler. And there is an epsilon parameter, which is a sampling frequency offset, and I will explain what that is in a little bit. So I'm going to put two channel models here, and let me make this clear. So this is receiver for antenna 1, and this is receiver for antenna 2. Okay, and what I'm going to do is to copy these two because it's convenient. So here what I have is GUI frequency sink, which is used to look at the signals received by each of the antennas separately, and then also the sum. So the idea of a beamformer is that we want to sum the signal of the two antennas or of many antennas. Here I'm using the case of two antennas as an example, but everything I'm explaining carries over to more than two antennas with no difference really. So channel model, we add the two antennas and we show this in the QT frequency sink. And I want to connect, I also have one of these. So virtual source. If you don't remember, we have used these virtual sinks and sources in one of the previous tutorials. The thing about this is that they are like a direct connection, but they can be used to keep the flow graph more tidy by not having these lines running all over the screen. So this is what I have now. And something I need to put here is a noise voltage. And let me check, what do I have? Okay, 1. So this is normalized for a noise voltage of 1. We have also used that in the past. And where is that important? This is important in, so we have here the wideband SNR. So this is important in the calculation of the amplitude to achieve this SNR. We have seen this formula before, maybe broken down into its components, but this is basically how you convert from let me see if I can show these. Maybe not. Okay, yes. So this is how, with this formula, is how you can compute the amplitude that gives the appropriate SNR. This is basically convert the SNR from decibels to linear units of power, and then we need to divide by the sample rate, which is the whole bandwidth of the noise in this case, and the sample rate needs to be divided by the wideband bandwidth, which is in kilohertz, so we have this conversion. This is nothing new. We have done things like this in the past. So, okay. What is very important here is there is this seed parameter on each of these blocks. And if you notice, any block which is able to generate random noise or any other kind of random signal has a seed parameter. The seed is used for the random generator. So if you use the same seed, you are guaranteed to get the same results. That might be quite helpful in simulations where you want to have reproducible results. Even if you are generating things randomly, you want that the same results happen when you run the flow graph multiple times. But in here, we need to be careful because by default, this channel model has a seed of 0. And we want to simulate that the noise added by the receiver in antenna 1 is different from the noise generated by a receiver in antenna 2. So the way to do that is to use different seeds, and it doesn't matter what number you use. So I'm just going to put seed 1 and seed 2. And in this way, the noise generated here will be different or uncorrelated with the noise generated here. And now I can show how this works. So I think I have some averaging on the GUI frequency sink. Let me see. Yeah, average height. So that's the reason why it's dropping down slowly. And you can see with an SNR of 0, we have the signal a few dBs above the noise floor. These blue and red are antenna 1 and antenna 2. If each of them is receiving the same signal power, and then we have beamforming. So I want you to think for a moment what happens when we have this beamforming, and beamforming is just the sum of these two. So we need to think about what happens with the signal, which is this part of the spectrum, and what happens with the noise, which is the rest of the spectrum. So what happens with the signal is relatively easy. We have basically the same signal, this astro signal, coming in through here, and it gets added. So the amplitude is going to be twice the amplitude here. Basically, I'm adding 2 copies of the same number. And increasing the amplitude by 2 is the same as increasing the power by 4, because power is amplitude squared. And if we express that in decibel units, that's an increase by 6 decibels. So maybe it's easier to show that when this has a high SNR, because if not, we also need to take into account the power of the noise in the SNR measurement. Here, we're not only measuring the power of the signal, but both the power of the signal and the power of the noise. But with a high SNR, the power of the noise is much, much weaker than the power of the signal. So here I have minus 14 point something, and here I have minus 8 point something, and that's a difference of 6 dBs as we expected. But then what happens with the noise? Because the thing is, by adding the signal from the 2 antennas, I'm hoping to increase the SNR. The physical intuition behind this is each of the antennas, imagine that it's a dish antenna, as in many radio telescopes, has a surface area which is used to collect power from the astronomical object. And then if I have 2 separate antennas, I should be able to sum the power collected by each of the 2 antennas, which is the same as summing the collecting area. So that's the whole idea behind beamforming. So then what happens with the noise? Because, okay, signal gets twice as much amplitude, but if the noise also gets twice as much amplitude, then we are not increasing the SNR because both the signal and noise would grow by a factor of 2 in amplitude. And what happens is that due to the fact that the noise here and here are uncorrelated, we do not get an increase in by 2 in the amplitude of the noise. We only get an increase by a factor of square root of 2, and square root of 2 is smaller than 2. So that's what gives the SNR increase. The way to think about this is as follows. We can think in terms of power, and when we have these uncorrelated noise signals, if we sum both of them, the power adds together. And so basically, if here the noise power is 1, and here the noise power is 1 as well, after summing both of them, the noise power is 2, which is 1 plus 1. And what happens with the amplitude? The amplitude is the square root of the power, so the amplitude is square root of 2. The mathematical reason behind this is basically variance. So the power of a random signal is the same as the variance, and the variance of two random variables which are uncorrelated is the sum of variances. So that's the mathematical detail behind this. But intuition, if you have two uncorrelated signals, then the power adds. If the signals are correlated, such as here for this astronomical source signal, which is the same signal arriving to both antennas, then the power doesn't add. What adds is the amplitude. And so we get an increase by 4 in the power. So let's check things here. Not sure if it's too clear to see. Let me switch this off. I have minus 44, and here I have minus 41. So there is an increase in by 3 dB in the noise. 3 dB is a factor of 2 in power, and that's what we expect. So to sum things up, we have two antennas. We are adding the signals from two antennas, and the signal itself increases by 6 dBs. The noise increases by 3 dBs only. So the difference, 6 minus 3 is 3 dBs. That is the signal to noise ratio that we gain by doing this beamforming combination. And this is what we would expect from a physical point of view, because the SNR increase is 3 dBs, or a factor of 2. And physically, as I mentioned, the idea is we are summing the powers from the astronomical source collected by each of the two antennas. In this example, the two antennas are the same kind of antenna, so they have the same collecting area. And then what happens is, by summing the powers, I'm able to increase the power by 2. So that matches our intuition. Here I'm choosing to add both signals. We could also decide to compute the mean. That's also a fair choice. It's the same as adding and dividing by 2. If I do that, then I basically get a different normalization on the noise and on the signal. So if I divide by 2, after adding, basically everything goes 6 dBs down compared to what we're seeing here. So the amplitude of the beamformed signal wouldn't change, and the noise will decrease by 3 dBs. That's another way of looking at this. It's just a normalization of the amplitude. Okay, so any questions at this point?
Yeah, I have a couple.
Sure, go ahead.
Yeah. So for the first one, this was just like a recap, but I was looking through the blocks in the flow graph, and I was wondering what exactly the polyphase arbitrary resampler does.
Good question. So here I have a noise source, and this noise source, every sample it generates is a random Gaussian variable. If I omit this, so probably the quickest way to do this is copy and paste and maybe even disable everything. Okay, disable, enable this one, and then have it copied, yes. So let me see, I want just one input. So if I only show the signal, then the noise occupies all the spectrum. And the reason for this is that if you generate random Gaussian variables and each of them is uncorrelated, so here it's a stream of samples, all of them are independent random Gaussian variables, then if you look at that in the spectrum, it will be flat. If I don't want the spectrum to be flat, I have two options. One of them is to introduce a filter, such as a low-pass filter, and that will introduce correlations between the random variables because a filter is doing sums, essentially. Or I can use this polyphase resampler, which basically does the same, but instead of a filter which doesn't change the sample rate, if I'm doing this resampling, I save some computing power by only generating as many independent random variables as I need. So if I now show how this looks like, you can see that the noise is limited to this portion of the spectrum, essentially because this block is taking as input what we saw before, which is noise occupying the whole spectrum, and then resampling that to occupy the whole spectrum. So if we resample by a factor of 10, we only get 1/10 of the spectrum, and the rest of that is supposed to be 0, but the filter is not ideal.
Okay. Cool.
Okay, so yeah, second question.
Yeah, I had a follow-up question. Not particularly for the polyphase resampler, but just for noise in general. You mentioned later on when we were summing the two sources that we introduced the seeds to ensure that they are uncorrelated. But my question was, if noise is randomly generated, how could it ever be correlated? And if it has a random chance of being correlated, how did the seeds ensure that the noise sources are in fact uncorrelated?
Okay, so perhaps you've used NumPy or C or any other programming language to generate some random numbers. When you do this with the computer, you can either specify a seed for the random number generator, or you cannot specify any seed, and then depending on the programming language, there is either a fixed seed by default or the computer clock, the system time is taken as seed. What happens is nothing inside the computer, unless you have a fancy hardware device, is really random. Everything is a deterministic algorithm. So the math that is happening here from the seed, which is 1, but it could be any number, is generating a completely deterministic list of numbers, which might look random because they keep jumping all over the place. But for sure, if you ever again start with the same seed of 1, you get the same sequence, exactly the same of seemingly random numbers.
Yeah, I guess my question was more directed on like how does that block like interpolate the seed like random generation? Because like I've seen it in like Python and other languages, but that's like there are like various ways to determine the randomness, whether it's like I think it's like milliseconds from some date in 60 and so on. But how does that block interpolate that to create like a signal?
So it's more or less if you imagine Python or NumPy, there is a seed. So seed NumPy, maybe I can. So imagine that block is C++, but it could be NumPy as well. It's calling this random seed with the seed that you are giving, and then it's calling this, where is it? There is something to generate the normal samples. So that's what's happening, but it's not NumPy, it's C++.
Okay, that makes sense.
And yes, the call here, so the normal call is called for every output sample. So every sample you need to generate for the noise, you basically draw another value from your random normal distribution.
Okay.
Okay, any other questions? Okay, so let's continue. This beamforming works great, but life is not so simple. There is a saying which says that in astronomy, everything moves. So what happens is that the Earth rotates, and so the apparent position of the source on the sky is moving. If you imagine we have these two antennas on the ground, let me, in fact, put them like this for a moment. And let's say that this is west and this is east. So this is like a map. I have one antenna on the west and one antenna on the east, and north is up, south is down. No surprises here. So the apparent position of the source on the sky will typically rise on the east. Then, assuming you are on the northern hemisphere, then it will go like this. It will transit on the south, and it will set somewhere on the west. Where it sets and rises depends on the declination, but you get the idea, right? So what happens is when the source is over here rising on the east, then the signal is coming this way and it arrives to antenna number 2 first, and then it arrives to antenna number 1 because it's traveling in this direction. And then what's going to happen is there is a delay. So the antenna 1 is going to receive the signal from the source with more delay than antenna 2. So I cannot really add these two signals together without compensating for this delay, because I will have unwanted effects. So I think that is quite clear. If you imagine the source can be anywhere on the sky, and usually the length that the signal travels to reach one of the two antennas will be different from the other. So that's one reason for a difference in delay, and that's what is called geometric delay. But there is also a second reason for a different delay in both antennas, which is cables and electronics. These two antennas need to be connected to receivers using cables, and those cables might not be exactly the same length. In fact, having cables which are exactly the same length up to a fraction of a millimeter is quite difficult to achieve, especially if they are long cables. And also electronics. Any piece of electronics will introduce a small delay on the signal, and the delays can be slightly different between different electronics. So we also have those instrumental delays, so to say. So what I mean here is, in general, the delay of the signal on the two antennas will be slightly different. So this is one factor we need to account for in our simulation, and we will also need to correct for in our beamforming. So that's one thing, but there are other effects we need to take into account, because, as I mentioned, the Earth rotates, and that means that if the source is initially here, it will apparently keep moving on the sky like this, and when it is on the south, here I'm using the example of one antenna on the west and one on the east. That's called west-east baseline, which is a simple example. But if I rearrange the antennas in any other way, the same can be said. Just the positions where things happen are different. So with this configuration, one antenna on the west, one on the east. If I have my source here, then the delay to both antennas is the same, because this is like in the middle of the two antennas. And then the delay to antenna 1 will be smaller than the delay to antenna 2. And the point I want to get across is that constantly over time, the difference in delay between the two antennas is changing. And changing delay over time is the same as a frequency offset. That's the whole reason why there is a Doppler effect. The Doppler effect comes because when you have a receiver and you have a transmitter, and there is some relative velocity between the transmitter and receiver, then the delay between the transmitter and receiver is changing over time, and that causes a frequency change. So What this means is that there is a small frequency difference between the two antennas because the source appears to be moving on the sky. How much that frequency offset is, it depends on the baseline length. It also depends on the observing frequency. It's usually a few degrees, a few hertz, sorry, at most, but nevertheless, it's important to take into consideration. So there's a different delay in each antenna. There is a different Doppler frequency in each antenna, and also the delay keeps changing over time. These are the three effects we want to model with this channel model. So let me rearrange these things and let me walk you through how to set the parameters here to simulate those impairments, basically. So what I'm going to do is to use the receiver for antenna 1 in the way it's currently set. I'm going to leave the parameters as such and only introduce frequency, delay, and delay versus time corrections or offsets in the receiver from antenna 2. Since I only care about the difference between the two antennas, that's enough. We could introduce changes in both channel models, but the only thing that matters at the end of the day is the difference between what we put here and what we put there. So I will put everything in antenna 2. So let me first explain how each of these parameters work. So noise voltage we already know. Frequency offset is self-explanatory. The only thing which is not self-explanatory is the units, and I hope these are here. Yes. Well, more or less. So it says the normalized frequency offset. 0 is no offset. Not .25 would be, for example, 1/4 of a sample time. What this is trying to say is that the units for this frequency offset are radians per sample. So that's the units we have here. Then there is this epsilon. Let me see what the documentation says. Sample timing offset to emulate the different rates between the sample clocks of the transmitter and receiver. 1.0 is no difference. So this is usually used to, as it says, to mimic what happens when I have a transmitter and receiver, and the clocks which are generating the sample rate on the transmitter and receiver are not going to tick exactly at the same rate, so I will get some sampling rate difference. This basically acts as a polyphase arbitrary sampler. In fact, this block combines a few other blocks behind the scenes. So the noise voltage is generated with this noise source. This epsilon is generated with the polyphase arbitrary sampler, and so on. This is just a handy way of having several parameters affecting the signal without the need of having a few blocks in the flow graph. So what is epsilon explained in better terms for what we are trying to do? I have said that there is a delay between the two receivers and the delay changes over time. So one way to explain what is a delay changing over time would be as follows. If we think about what happens during 1 second, then antenna 1 is going to receive 1 second worth of signal from the astronomical source, which is 1 million samples. But then antenna 2 might receive slightly more or slightly less. And the reason for that is because if the delay is changing, then the time that it takes the signal to reach from the transmitter to the receiver will keep changing over time. So what is 1 second worth of signal for receiver 1 might be slightly more or slightly less for the receiver 2. And how that changes is controlled by this epsilon. The units are the same as in the resampling rate. So this is how many how many output samples are produced for each input sample. And by using that, we control the delay. So for example, if I set this to something like this, what is going to happen is that this is generating slightly more samples than this one. So when I'm adding the samples together, these will appear to fall back behind because I'm adding 1,000 samples from this, or any number of samples from this. I'm adding the same number of samples from this one, but for example, let's do the example with 1,000. So to generate 1,000 output samples, this block needs 1,000 input samples. However, to generate 1,000 output samples, this block needs slightly less than 1,000 input samples. The reason is this epsilon is slightly larger than 1. So then what happens is this signal is going to keep falling behind and behind because this is, let's say, 999. This is only taking 999 samples for each of these 1,000 samples. So here I have one extra sample. And that is an extra delay, which will keep increasing over time. So that's how this works. It will be much clearer when I run this with the appropriate parameters. And then there is the TAPS parameter. TAPS is used to simulate multipath. So that's what happens when the signal reaches the antenna through separate paths because there are reflections. That is often used in terrestrial communications because you can imagine signals bounce off of buildings, mountains, walls, depending on where you are. So the same signal could arrive the receiver as well as echoes of that signal which have been reflected somewhere. In radio astronomy, that is often not the case because we aim our telescopes directly to the astronomical source and there is really not much in the way to cause reflections. So this is just so you know what this TAPS parameter is for. Okay, so let me see what I have here. I'm going to copy and paste a bunch of entries to save me the effort of introducing this. And basically we have the phase difference in degrees. This is going to be the phase difference between the two antennas. I haven't spoken of phase difference, so I should at this point. If we have a difference in delay, we will also have a difference in phase because the carrier phase is affected by delay. You can think of the signal, it's modulated on a carrier wave, and then if I change the position of my antenna or if I change the delay, the number of carrier wave cycles that the signal needs to travel through to get to the receiver is different. So there is also a phase difference. This is the frequency difference in hertz. This is the delay rate difference in parts per million. Parts per million is a common unit when you are dealing with things which are very small or very close to 1, as in this case. So this is going to be 1 plus a very small number. And what is a part per million? For example, 1 part per million would mean that for every 1 million samples, an additional 1 sample of delay is being accumulated. And another way of thinking about that is every second, 1 millionth of a second, which is 1 millisecond of delay, is being accumulated. So that's delay difference. And then delay rate difference, sorry, this is the derivative of delay. This is how delay changes over time. And then there is delay difference, which is in samples. So to introduce this on the flow graph, I don't want to make mistakes on the formula, so I'm going to copy and paste these two and then explain the formulas. Okay, so the frequency offset is a very simple formula. The frequency difference we have is in hertz, this frequency difference. And then this frequency offset, I said it was in radians per hertz. That's not correct. It is in cycles per hertz. Sorry, in radians per sample, but that's not correct. It is in cycles per sample. So this is in hertz, which is the same as cycles per second. This is in samples per second, and so the quotient has units of cycles per sample as needed here. Then for epsilon, we have 1 plus a very small number, which can be either positive or negative. And parts per million means that we need to multiply by 1e minus 6, which is 10 to the power minus 6. And then for the taps, good point here. So the taps is usually going to be a list of complex numbers. This is what is meant here by complex vector. And each of the elements on that complex vector represents one echo of the signal, with the first component of the vector representing the direct signal. And those are complex numbers which have the amplitude and phase of the signal. So in this case, I don't want to generate any multipath, but I want to use this as a way to change the phase of the signal. We could also multiply by this complex exponential with a multiply constant block, but by using these tabs, I can do everything on the same block. So this is just an exponential, and I'm converting the phase in from degrees to radians, because the exponent of the exponential needs to be in radians. So this is the parameters we have here. And let me show you how this looks like on when I run the flow graph, and then I will stop for questions. So I'm going to play this. And like this is as we had before, because we have adjusted the phase difference to 0, frequency difference 0, everything is 0. So this is the ideal case when the same signal is arriving to both antennas. So then let's see what happens with each of these parameters. The easiest to understand is the phase. So let me, for example, set a phase of 90 degrees and watch what happens with the beamforming signal. It has decreased slightly. And the reason is before we had the same signal coming in here and here. So when we add them, the amplitude increases by a factor of 2. However, if we have a 90 degrees phase offset between these two signals, then the amplitude is not going to increase by a factor of 2. It will only increase by a factor of square root of 2, because of basically what happens if you add two vectors which have the same length and are at 90 degrees apart from each other. So in this situation where I'm trying to add together the signals from two antennas, but there is a phase difference of 90 degrees, I get no SNR increase because the signal also increases by 3 dBs. But we can keep going further. For example, 120 dB, 120 degrees. Now you can see clearly that there's an SNR loss, and if I go to 180 degrees, the signal disappears. Remember that 190 degrees of phase is the same that as changing the sign. So what is happening here is here I have some signal and here I have the same signal with the opposite sign. So when I add them together, the signal disappears and only the noise remains. So what this tells us is that when we do beamforming, we need to be careful and arrange things in a way so that the phase difference of the antennas is at least close to 0, and ideally as close to 0 as possible. Otherwise, we do not get this amplitude increase by a factor of 2 that we wanted. What happens with the frequency difference? A frequency is just the change of phase versus time. So for example, if I set here 0.1, then when I hit enter, the phase difference will change, and every 10 seconds it will complete 360 degrees. So we are going to see the same thing I was showing before, just changing continuously over time. So I press enter, and now what happens is the signal is decreasing. Now there's cancellation, so now the offset is 180 degrees. And again, the signal is increasing because now they have more or less the same phase. So this is how a frequency offset looks like. You have cancellation and addition of the signal changing over time. We can revert this to 0. How does delay difference look like? Let me explain the delay difference before delay rate difference. So I'm going to make this one sample, and maybe this is not so easy to see. So what I'm going to do is to put this at 0. What happened? I had some division by 0. Oh, I wanted to change this one, and I changed the bandwidth here. So what I want to show is what happens with a wider signal. So for example, 750 kilohertz. And now I'm going to set a delay of 1 sample, or maybe even 2 samples, or even 10 samples. Let's see. Okay, with 10 samples, it's clear what happens. Let me disable this. So alternatively, in frequency, we have addition, then cancellation, addition, cancellation, addition, cancellation, etc., etc. And the reason for that is that a delay is the same as a phase change that depends on frequency, and it depends on frequency in a linear way. So something that you need to remember when you are thinking of multiple antennas and interferometry is that a delay is the same as a phase slope versus frequency. This will become more clear when we do something to plot the phase difference of the signal. But you can imagine that what is happening here is at some particular frequencies, this delay causes a phase difference, which is close to 0. And so the signals add together. And then at some others, there is cancellation because the phase difference is 180 degrees. How many peaks and troughs I get into this pattern depends on how many samples I set here. Basically, I will get over the whole bandwidth I have here, I will get 10 periods of this pattern. So you can see, for example, if I set 20 here, then I get twice as many. So that's the reason I was trying to look for a number where things are easy to see, because with 1, it's not so easy to see. I think the maximum is in here and the minimum is here, so we don't really see it. And then with 2, we get a couple minimums here. With 3, now we can see it more or less. So 1, 2, 3. So this is how a delay difference looks like. Of course, it's an unwanted effect because it changes how our signal looks like. How does a delay rate difference look like? It's the same thing. If I set here, I don't know what's appropriate, maybe 1, then what will happen is we will see the same thing as before, but increasing over time. So you can see delay is increasing, and the number of peaks and troughs we get on this graph keeps increasing. So that's how a delay rate appears. And if I set this to 0, the change stops, but we have already accumulated a delay of however many samples here. Okay, any questions? Great. So what we have seen is when we try to combine the signals from two antennas or perhaps more antennas in the real world, there are these unwanted effects. So there are phase, frequency, delay, and delay rate differences between the two antennas that we need to take into account, or otherwise something like this will happen. So before doing beamforming, because beamforming is adding just the two signals from the two antennas, we need to correct for the phase, for the frequency, and for the delay. And the way to do that is we have two reasons why there is all these effects. One of them is pure geometry. So if we know where the source we are observing is on the sky, we have some ephemeris. So for example, right ascension and declination, and we know the locations of our antennas, then we can compute what I was saying before. So let's pretend the source is here, and then the signal takes some time to reach to this antenna and some other time to reach to that antenna. So that can all be calculated because the positions of all the objects is known. But there are also instrumental effects caused by the receivers, the cables, and even things such as the atmosphere. So if the antennas are separated enough, the part of the atmosphere through which one of the antennas is looking at the source can be slightly different compared to the atmosphere above the other antenna. So the atmosphere might also introduce a slight delay difference between the antennas because the atmosphere introduces a small delay on radio waves, which depends on things such as humidity and temperature. So you can imagine that these things can change and can be unpredictable. So because there are some unpredictable effects, I've mentioned the atmosphere, but also electronics, everything which has analog electronic components will introduce these effects, and often they are temperature dependent, so they will vary slightly over time. So the point I want to make is that this requires a calibration of the telescope. We need to figure out what is the phase difference, frequency difference. Often there isn't a frequency difference, at least if we are using the same frequency reference for all the receivers. And there is also not a delay. By there is not, I mean there is not an instrumental frequency difference. There is a geometric frequency difference, but that we can compute using the known positions of the antennas and the source. There is an instrumental delay difference. You can think the cables are different lengths, and moreover, their delay depends somewhat on temperature. So that's the reason we have this, and we need to measure it and calibrate it. And then the delay rate difference, usually we do not have an instrumental delay rate difference, but we have a delay rate difference from the geometry, from the apparent position of the source on the sky. So the question is, how can we measure basically phase difference and delay difference, which are the parameters we need to calibrate for? And then this is going to be done with FFT. So I'm going to copy all of this and then explain it. And I also need these two. So, and I also need these for antenna 1 and antenna 2. So what we are doing here is we take the signals from antenna 1 and antenna 2. We compute FFTs for each of the two signals. And with one antenna, we have done this to show the spectrum of the signal. Then we would have complex to magnitude squared blocks. So the complex to magnitude squared to convert from complex numbers which have phase information to magnitude squared, which is only power. So this is what we have been doing so far. However, what we do here is we do multiply conjugate. And this is a way of looking at the phase difference between the two antennas and of doing that over a set of different frequency bands. Why over a set of frequency bands? Because we have FFTs, so the output of this is vectors, 256 points in this case. So basically, I'm dividing my signal in these 256 FFT bands. And in each of them, the signal is going to have some phase in each of the antennas. And when I multiply the complex value from one antenna by the complex conjugate of the other antenna, I'm extracting the phase difference information. And the reason is, if you think about complex exponentials, the phase is the thing that goes on the exponent together with the I number. And then if you take the multiply conjugate, you need to change I by minus I, and by multiplying, the two exponents are added, but since we have changed I by minus I, the two exponents are subtracted. So whole summary of this thing, if you ever see multiply conjugate, that's the same as doing a phase difference of two complex signals. So that makes sense because we want to measure the phase difference between the two antennas, and having these FFTs to see what happens over frequency also makes sense because we have seen that a delay is the same as a phase slope versus frequency. So by doing this analysis over a set of frequencies, we can figure out what the delay is. By the way, because maybe you will hear this word in other contexts, this kind of thing, basically these two and the integrate block are known as an FX correlator. So if you ever see this FX, that's what it means. The F means FFT and X means multiply and integrate. So this is a correlator. We use a correlator to look at the signals from the two antennas and figure out this phase and delay difference. How do we do that? So the thing I'm showing here is I'm integrating. The reason to integrate is the same as when we were computing a spectrum of just a single antenna. It's to average things together and remove noise. What happens here is with the multiply conjugate, I'm only extracting the phase difference information, and phase difference is going to change slowly over time, so I can integrate. Without this multiply conjugate, I could not really integrate because the output here is somewhat random, and then if I integrate, I basically the integration averages out to 0. So that's what happens. And then I'm going to show the result of the FX correlator, so of this integration, in two different ways so that we can really understand what happens. The first way is in the frequency domain. So to do that, I want to show the phase, and the phase can be obtained with this complex to argument. Argument is the argument of a complex number. So this will give me the phase, and we have the trick with repeat because what's the integration time here? 100 milliseconds. So anyway, the repeat is useful to have this block update quicker. And then I also want to look at this in the time domain, which is also called lag domain, because as we will see, it speaks about the delay, and another word for delay is lag. We could also say time domain here or delay domain, both would be appropriate. So here I'm in the frequency domain to show the time domain, I need to do an inverse FFT, and the inverse FFT is done by putting here reverse, and I have here a window rectangular, but this could also be like this, an empty window. This is the same as here. And then again, the trick with repeat, complex to magnitude, it doesn't matter the order of these two operations. They could be switched either way. And then the vector sync to plot. And this scale is for the plot, I guess. Where is it? Yes, Y maximum. So let's run this and see what happens. We have here a frequency domain phase, and what we see is there is noise all over the place in most of the spectrum except where our signal lies. And that is to be expected because outside of this part of the spectrum, the thing we have is random noise, which is different for both antennas. So when we compute the correlation, this FX correlator thing, we are going to get a random phase value all over here. However, in the part where I do have a signal, and let me make that somewhat larger, in the part where I do have a signal, we can see that the phase difference is very close to 0, and that's to be expected because I have set my phase difference at 0. If I put 90 degrees here, then the phase difference goes to minus 1.61 radians, which is supposed to be minus 90 degrees. Here there is just a sign convention somewhere, so depending on which of these two antennas goes to the conjugated input of this multiply, and depending on whether I apply these things to antenna 2 or to antenna 1, I would get one sign or another here, but it doesn't really matter. So my point is, by looking at this thing on the output of the correlator, we can measure what is the phase. So let's pretend I'm setting up an observation at the telescope, and there is an unknown phase difference between the antennas because of the electronics and everything. So what I do is I point the telescope to what is called a calibrator source, which is a wideband source. It doesn't occupy 300 kilohertz. It occupies all the spectrum. And what I do is to run a correlator and look at the correlator output to see the phase difference. In doing this, I need to compensate for the effects of which I already know, which are the geometric delay from the source to the antennas. But anything which is unknown, such as this instrumental phase difference, can be measured on the correlator. So this is how the correlator can help us measure a phase difference. How can it help us measure a delay difference? So let me put maybe one sample is not enough. So let me put 4 samples here. And what's going on? Let me have it done something wrong. I'm wondering. Let me see. Okay. Yeah, somehow I don't see the effect I expected here. I expected a phase slope versus frequency, which is the thing which is causing this. So I have probably made a silly mistake. Oh, I see. Yes. So my silly mistake is I did the antenna 2 connection before applying the delay. So of course things didn't work. So let me go back to that. We have this 300 kilohertz signal, and then if I put, for example, 5 samples, we get this linear slope. So we can see that the phase difference between the two antennas depends on frequency. And in here is 180 degrees, or rather minus 180 degrees. It completes a whole 360 degrees cycle in a matter of, I don't know how much this is, 200 kilohertz, I guess, yes, because it goes from minus 100 to plus 200, from minus 100 to plus 100. So in a matter of 100 kilohertz, it completes a cycle, and then we see another half cycle, and here the signal stops. So that's the only thing we can see, but if we make this signal wider, we can see the whole pattern. So that's how a delay looks like. If you see this slope, then that means we have a delay. And let me auto scale on this one. So this is on the frequency domain. On the lag domain, we can see there is a peak, and this is called correlation peak. And the location of the peak is the delay in samples between the two antennas. So here, because of unit choice, this is the FFT size is 256. So delays which are close to 256 are really meant to be negative delays. So these 251 samples is the same as minus 5 samples, because 256 minus 5 is 251. So we can see that this is no coincidence. In fact, for example, if I set it to 1, the peak here is on 255. And let me see if I can set minus 1. Yes, I can. So if I set minus 1, then the correlation peak is at 1. If I set minus 15, for example, the correlation peak is now at minus 15. And I should get here 15 phase wraps. These are called phase wraps over the whole 1 megahertz bandwidth. So this is how we can measure delay on the correlator output. And just for fun, what we can see is how a combination of all of these effects affects the correlator output. So here I have a frequency difference, and we can see the phase is moving over time. And if I also set delay rate difference, so for example, something like this, we will see that over time, the slope of the phase is increasing and increasing. And we can also see here in this correlation peak plot how the correlation peak is moving. And as time goes, it will keep moving and moving. So this is basically the way to measure all of these parameters using a correlator. Once we have measured them with the correlator, we basically apply the correction for this, which in GNU radio would be something very similar to a channel model. And once we have done that correction, we can add the signals from the antennas, which is the beamforming step. So that's how a beamformer actually works. Questions? So for the second part of today, I have this beamformer array demo, which I already have open, and this I'm not going to do from scratch because it's a large flow graph and it's quite repetitive. So this is a demo of something which is called a linear array, and for that I have this image from Google. So a linear array is one of the most simple kinds of arrays of antennas, because all the antennas are placed in a straight line, and the distance between them is the same, and this makes the math so much easier. At the end of this tutorial, we will talk a little bit about how things change if you have the antennas in another configuration. So here there are 4 antennas in this diagram. In the flow graph, I have 6 of them, but it doesn't matter. You could have only 2 antennas or as many as you wanted. The thing that changes is your beam width, your synthetic beam width, and we will see what that means in a minute. So we have a signal, and it's originated from a source which is very far away, and that means that the signal arrives on these parallel rays to all of the antenna elements. And then we can ask ourselves what is the difference in delay. So you can see here that ray 1 is the first to arrive to one of the antennas, and then ray 2 arrives to this antenna slightly afterwards, and the extra delay is given by the length of this segment. So the difference in delay depends on this angle, which here is called theta, because you can imagine that if the source is here or like overhead, then the rays will be completely down, and the signal will arrive at the same moment to all of the antennas. But in general, for this angle theta, what happens is if we call d the distance between 2 antennas, then this is a right triangle. As you can see, this is the right angle of the triangle. So doing some trigonometry, if this side is d, then this side must be d cos theta. And what happens with this antenna? What happens is basically the same, but we have a larger triangle, and the side here is 2d because there are these 2 separations. So this is 2d cos theta, and then this is 3d cos theta. So very well, that's basically what happens depending on the angle to the source for a linear array. And why should we care about that? We care about that because the extra delay here is something we need to correct for when beamforming. We have already seen that, but it also allows us to do something quite interesting, which is beam steering. It's called beam steering. And that means that by changing the phase correction we apply to the antennas, we are able to change the place on the sky we are looking at. We are able to steer the beam we are forming. And since all of this is digital, here we are using GNU radio, for example, in this beamforming demo. That means we can have many copies of this beam steering algorithm. So anything which our dishes can receive, we might be able to point many synthetic beams to different points in the beam. So to give a better example, for the ATA, for the Allen Telescope Array, the dishes are 6 meters wide. That means that depending on the frequency, the beam width of the signal might be a fraction of a degree, let's say a quarter of a degree, for example. And then that means that when we point these dishes from the sky, anything which is in that area of 1/4 of a degree around the position where we are pointing the dishes gets into the antenna because of how the antenna beam is. Then what we can do is to beamform, so that will give us a much narrower beam by combining the signal from all of the antennas in the array. But since that is a digital process, we can do it as many times as we have computing power for that. And you can imagine, for example, if we are doing a SETI search inside this 1/4 of a degree area where the antennas are aiming, there might be many interesting stars that we want to observe. So we can do beam steering and point one synthetic beam to each of the stars which are within the primary beam of the antenna. The primary beam is what is determined by the physical size of each of the antennas in the array. So that's the point of this demonstration. And how does this look like? I basically have, let me zoom out all the way. This isn't it, so beamformer array demo. I have here two signals. This is the same as before, Gaussian polyphase arbitrary sampler. So astronomical signal 1, astronomical signal 2. And the reason why I have two signals is because I'm going to simulate that they come from different parts of the sky. By once again going back to this graph, one of them will have one angle, let's say theta 1. The other one will have a slightly different angle, theta 2. So we have these two Gaussian signals, and then on each of the antennas, and there are 6 of them, the two astronomical signals come in. Each of them is subject to a phase shift. So for the first antenna, I have 0 here, and then antenna separation is what was called D in the diagram. And then I have, let me make this larger. I have the sine of the signal angle rather than the cosine, and the reason is this is measuring the angle from, let's say, from the horizon, from this horizontal line. I want to measure the angle from the vertical, so this would be the angle for me, and then rather than have cosine of theta, I need sine of theta, but that's just a minor detail, so I have sine of theta of my signal angle. So that's the phase that happens, the phase shift that happens because of this geometric delay. For the astronomical signal 1. The astronomical signal 2, since in general is in a different part of the sky, has a different phase shift and everything looks the same, except here we use signal angle 2. So we have the two signals, each of them with its own phase shift. We also have Gaussian noise, and we add all of these three together. And then we have the beamformer. And here we are going to have two beamformers, since we want to be able to point each of the two beamformers independently. And for example, we might point one of the beamformers to the astronomical signal 1 and the other one to the astronomical signal 2. So the beamformer is nothing more than a phase shift, which is intended to compensate for the phase shift here. So it's practically the same as before, but there is a minus sign in front, and then there is beamforming angle. So beamforming angle is something else which is defining one of these GUI entries. So to show this, there is signal 1 angle, signal 2 angle. These in general we do not choose. Here we are able to choose because this is a simulation, so we can choose all the parameters, but in real life these will be the positions on the sky where the sources are physically located. But what we can choose is the beamforming angle. So beamforming angle for beamformer 1, beamforming angle for beamformer 2. These are variables that only affect the digital computation we do in the beamformer. So even in real life, we can choose them however we want. So antenna 1, antenna 2 is basically the same, but instead of 0, there is a 1 here. This 1 is because of this 1D. And you can see that if I go to the next antenna, there will be 2 because of 2D. So antenna 3 here has a 2D, and so on and so forth. So the same antenna 2, antenna 3, antenna 4, antenna 5, antenna 6. If I zoom out all the way, you can see I have this structure with 6 antennas which are identical except for the parameters here: 0, 1, 2, 3, 4, and 5, right, for the antenna separation. And then the output of all of these, sorry for changing the zoom. The output of all of these is added for the first beamformer, and the output of all the phase shifts for the second beamformer is added as well, and then we have a GUI frequency sync. So this is the flow graph. The rest is the parameters of the two wideband sources, which are simulating each astrophysical signal, astronomical signal. And then something else we need to define is this antenna separation, this value D. And this is in wavelengths units, because here I'm doing things in radians for the phase, and I'm not taking carrier frequency into account. So that means the antenna separation is in wavelengths. So 100 wavelengths. We will speak in a moment about how the antenna separation affects the beamformer. So if I run this, then what happens is at the moment I have the same values on beamformer 1 and beamformer 2. So let me disable beamformer 2. I have the two signals. So signal 1, let me see which this is the one which is at 50 kilohertz. So this one. Signal 2 is the one at minus 150 kilohertz, so this one. And I could change each of these as I wanted. And then I have set by default both of the signals to an angle of 0, and my beamformers are both set to an angle of 0. This is really the same thing we were doing in the previous flow graph, because we are not applying any phase shift to the signals from the antennas, and we aren't doing any phase shift in the beamformer. This corresponds to the situation where the source is above, like here, and it arrives at the same time to both antennas. So then let's take one of the signals, so for example, signal 1, and start changing the angle. So if I make it, let's see, 0.02 degrees, then we cannot see much change. Let's see, 0.05. Now it has certainly decreased. And now if I set here, for example, 0.075, smaller again, and 0.1, now it's basically below the noise. And let's make it larger. So for example, 20. No, that's not the one I wanted. So 20. To be able to see what happens very clearly. So here is when the signal angle is 0 degrees. If I put 0.1 degrees, then I see a huge decrease in amplitude. If I do this, then it increases again, but it doesn't get quite to the original level, which was something like this. If I do 0.2, then it drops down again, and I can continue doing things. And depending on this angle, we basically have one thing or another. So what is happening here? The thing that is happening is that when the signal angle is the same as the beamforming angle, we get all the amplitude increase from the beamformer. We can say that the beamformer is aiming towards the signal, and then that's when we get the maximum amplitude. When the angle begins to increase, such as for example 0.1, we see a huge decrease in amplitude, because now the phase shifts we are doing in the beamformer no longer cancel the phase shifts from the geometry of the astronomical signal. And so when we add all of these 6, there will be some cancellation. So that's what happens when the beamformer is not aiming directly to the astronomical source. And then one might ask, okay, depending on the angle, how does the amplitude we get look like? We have seen that for angle 0, the amplitude is maximum as expected. For 0.1 is very small. For 0.2 is slightly larger again. And the thing is that the amplitude we get is called the synthetic beam pattern, and it depends on the shape of the array. This is the most simple example of the array. So the amplitude we get is basically a sinc function, which in dBs looks something like this. So let me show this in full size. So when we are aiming the beamformer towards the source, then we get the maximum amplitude. As we move away, the amplitude decreases. And you can ignore this blue dotted line. I'm concerned about the red line. So as we keep aiming away from the source, there is some point at which it disappears. Then it comes back again, and this is minus 13 dBs. And there are all these things which are called side lobes. But the most important thing to remember here is only the maximum amplitude is achieved when the direction of the source or the angle of the source matches what the beamformer is synthesizing. So why is this useful? This is useful for several reasons. One reason is that, for example, it can help us separate different sources on the sky by beamforming on one of them. So the way I can show that is, for example, let's pretend this is at 0.5, and let's put it back to a more reasonable amplitude. And what happens is, if I set my beamformer to 0.5 degrees, or maybe even let's make it 5 degrees. That doesn't matter, so let's keep with 0.5 degrees. So the point is, now I have two sources on different parts of the sky. One is at 0.5 degrees, the other one is at 0 degrees. And by using two beamformers, one of them pointing to 0.5 degrees, the other one pointing to 0 degrees, we can separate the two signals. You can see that here beamformer 1 output is stronger on the first source, whereas beamformer 2 output is stronger on the second source. If in this case, it's quite evident because the two signals occupy different parts of the spectrum. But if I increase the bandwidth to make this much larger, and also here, for example, this is the frequency, so I didn't want to touch that. I wanted to touch this thing. So for example, like this. In this way, we are able to separate the signals. So you can see on one of the beamformers, we can see the blue signal better than the red one. And on the other one, we can see the red signal. So that's the point. We can aim to different objects in the sky and separate their signals. What factors affect what happens in a beamformer like this? One of the important factors is the antenna separation. So this D here, and also the number of antennas. What happens is that the resolution, the spatial resolution of a beamformer is related to the maximum separation of the antenna. So in this example, it will be 3D because we have 4 antennas and the maximum separation is between these, which are 3D apart. In my example, it would be 5D. And what happens is the farthest apart you have the antennas, the narrower your synthetic beam will be. So if I go back to this plot, I haven't talked about the units in this axis. This is basically if I'm doing radians for the angle, this is basically 1 divided by the maximum antenna separation. So in this example, let's work out the math. I have 6 antennas. They are separated by 100 wavelengths. So 6 minus 1 really, because the maximum separation is 5 distances times 100. And 1 over this is my beamformer resolution in radians. If I want to convert this to degrees, I can do like this. And you can see it's basically not 0.1, or rather not 0.15, which is basically what we saw before. So if I remove source number 2, let's make them 50 and 50 to have them separate. So what I mean is if I copy the number from there, not 0.1145, not 0.1145, that's, as you can see, basically the location of the first null of the beam pattern. That's where my signal disappears. It means that everything which is less than 0.1 degrees from the beamformer position will show up in the beamformer output to some extent. Everything which is farther away will be much more attenuated. So that's what happens, and this is determined by the separation of the antennas. Depending on how many wavelengths the antennas are separated, then we will have one beam width or another. And in this case, 100 is for the sake of the example, but oftentimes antennas are separated by thousands of wavelengths or tens of thousands of wavelengths, or even millions of wavelengths, or much more if we are doing VLBI. And that gets us a very narrow synthetic beam width. So that's something to take into account. What else? How does the number of antennas affect what happens? Because here I have 6 antennas, and in here I have 4 antennas. So what would be the difference? And the difference is basically a matter of side lobes, really. The pattern will depend on the number of antennas, and the most antennas I have, the better. There will be less side lobes. Having more antennas is also better for SNR because we have more collecting area, but it's also good because of side lobes. So that's how the number of antennas plays a role here. Do I want to show something else with this example? Maybe not. Questions at this point?
I've got a maybe logistical one about the number of antennas. With only 6 in this example, it's a pretty big flow chart, and I can imagine that it would get kind of annoying to pan around it and change parameters if you had to do that. And if the ATA is like a factor of 6 or 7 more antennas than that, I don't know, it just seems kind of inconvenient. Is there any way to I guess streamline the flow chart if you have an array with a number of antennas on the order of the ATA, or even like DSA 110 or DSA 2000?
Yeah, good point. So at some point, the flow graph itself is going to be a limitation for you, because if you want to have a huge number of objects here, is going to be cumbersome, as you imagine. There are some tools which can be used to your advantage, and one of them is what is called hierarchical flow graph. So let me mention what is that. We haven't used that, but there is something called higher block. And the way this higher block works is that you can have a flow graph which then gets built as a radio block that you can use as in another flow graph. So rather than having all of these, I could replace all of these blocks by a hierarchical flow graph which contains these blocks, and then I could instantiate the hierarchical flow graph for each of the antennas. So rather than having, I don't know, 6 blocks per antenna, I would have just one of them. And certainly that avoids a lot of repetition. But even so, if you are going to have 42 antennas or hundreds of antennas, or who knows, having 1 block per antenna is not a good way to do it, because it's still going to be cumbersome. And in fact, what I think is that trying to have a flow graph is going to be a limitation in this case, because if you try to have hundreds of antennas in a flow graph, it's going to be cumbersome one way or another. So what you can do is Python code. As we have seen behind the scenes in a GNU radio flow graph, there is a Python script that gets generated. You could write a Python script from scratch, or you could use the Python script generated here as an example. And then by using Python, you can do things programmatically. So rather than dragging and dropping blocks for each of the antennas, you could have a for loop. And you say for each of my antennas, and Python doesn't care if it's 6 antennas or 1,000 antennas, instantiate all these blocks and connect them. So anytime I have something which is unwieldy as a flow graph, I do a Python script. We lose the advantage of being able to see how the flow graphs looks like and of editing things easily, but however, we gain much flexibility by going to Python.
That makes sense. Thank you.
Other questions?
How would you model the phase delay for antennas that aren't perfectly in a line?
Good question. So I wanted to get that, and now it's a good moment to do that. So if we go back to this diagram, basically the basic math is the same. What changes is that the formulas are not so nice anymore. So if I have my antennas somewhere else, you can still compute how what is the length of each of these segments, which is the extra delay. That's basically the only thing you care about. And in the end, that's a problem that you can reduce to what's the location of the source, the area and deck coordinates, if you wish, what's the location of the antennas. These are going to be fixed to the ground. So usually you use longitude and latitude, or something called ECEF coordinates, which means Earth fixed coordinates. And you also need to know the time, because Earth rotates. So by basically doing vector math, you can compute all of these from area and deck and antenna positions. What happens is we do not have this nice expression anymore. And I want to take a second to explain why this is nice. So the thing why this is nice is this sign of the signal angle. You can think of this as a small number because the signal angle is going to be small. So there is the small angle approximation, right? Sine of a small angle is more or less the same as the angle itself. As an approximation, I could put signal angle here. And then basically I have 0 times 2 pi times something multiplied by the angle. 1 times 2 pi times something multiplied by the angle. 2 times 2 pi times something multiplied by the angle. And this looks very much like a Fourier transform. And in fact, it is a Fourier transform. So what happens behind the scenes, behind beamforming, is that the Fourier transform is always present because of how these phase delays act. In the case of a linear array, so that's what is nice about the linear array as an example, you really get a Fourier transform. So you really get a Fourier transform of, in this case, a 6-point Fourier transform of the angle, of which angle of the angular error. So that means if I'm beamforming to 0.1, for example, and my source is 0.12, the angle error would be this 0.02. And this is the mathematical explanation for why we get this sync pattern. This is how the Fourier transform enters the picture here. So coming back to your question, what happens when you have the antennas not in a nice straight line, but scattered on a field, is that yes, there is the Fourier transform as well, but we do not get a nice one-dimensional Fourier transform, as in this case. We get a two-dimensional Fourier transform, and we only get it at evaluated at certain points. And I want to make a connection, which I was going to make anyway, with interferometrical imaging. Probably you've seen the images that are made with radio telescopes, and you might be wondering how these images are made. There are two ways of making an image of the sky with a radio telescope. If your telescope is very, very large, and I'm thinking of a Green Bank telescope, which is 100 meters, the beam width is so narrow that you can move the telescope across the sky, measure the power of the signal in different points of the sky, and that will be your image. So you are directly moving the dish and computing a heat map of received power versus antenna pointing. But if your telescope is not 100 meters large, if your telescope is an array of small dishes, that doesn't serve because the primary beam of each of the dishes is too large. So what you do is interferometry. You compute phase differences. Basically, amplitudes are also important, but today I'm mostly speaking about phase differences. So coming back to these FFTs, you have an FX correlator. You compute these kinds of things, and those correspond to evaluating the Fourier transform of the image that we want to see at some points in the plane. It is a two-dimensional Fourier transform because the sky is two-dimensional. And which points we get this measurement at are determined by where we place our antennas. So oftentimes antennas are not placed randomly, they are placed having in mind achieving good coverage of these measurements, which are on a plane which is called the UV plane. If you ever hear the expression UV plane in interferometry, that's what it means. And then we basically do an inverse FFT transform. One way of thinking about that inverse FFT transform and interferometry in general is that we are doing beam steering with a beamformer for each pixel in the image that we want to obtain. So here, if I wanted to make an image of the sky, this simulation is one-dimensional. So I would get a one-dimensional image, but you probably get the idea. What I do is I keep changing this value. I put 0 and hey, there's a source there, so it should appear at 0 degrees on my image. Then I keep moving, and by seeing how the power changes, that's how I make an image. And in real life, I would make this with 2 variables because the sky is a plane and it has 2 variables. However, if we want to have one beamformer for each pixel in the image, that's going to be very computationally intensive. So you can think of this UV plane, FFT, and so on and so forth as a way to have a beamformer on each pixel of the image, but in a way that uses FFTs to be much more mathematically and computationally efficient. So sorry for the long answer. That was kind of roundabout, but those are things I also wanted to explain today, and hopefully it answers your question. If not, just let me know.
Yeah, that makes sense. Thank you.
Okay, more questions?
In the case where you have a two-dimensional array of antennas, how does that change your geometry and delays as opposed to just having like a one-dimensional array?
Are you thinking about the regular kind of array, such as if you have a chessboard and place one antenna in each of the squares, or something more randomly placed?
Yeah, or like with this array where all the antennas are in a line, but if the source was
Okay,
in the second dimension going into the screen instead of off to the left or the right.
yeah, I see. So the same picture, but the source is out of plane. Then what happens is you can project all of this into this 2D plane, because what happens in the into the screen direction doesn't matter. It only matters what happens along the direction of my array. Since here the array is one-dimensional, then I don't have a good 3D plot, but you can probably convince yourself by trying to sketch this on paper that you only care about this projection on this screen plane. If the source was offset from the screen, then yes, it arrives slanted to the antennas, but that slant doesn't contribute any additional delay difference. Only the angle theta here is what matters.
That makes sense. That makes sense.